What does differentiation mean? I have thought about it. No, but that's a good thought, just logically deducted. I like that, but no. Differentiation means that it's the derivative can exist of that function. So what does a derivative tell us? The slope of the line tangent to a curve. It also tells us the rate of change that something's occurring. Because we're going to learn today what it means in the real world. It doesn't mean slope, doesn't mean rate of change. It means other things to it than that. In order to be differentiable, what conditions have to exist? To be differentiable, which what again? Very good. A function must be continuous. But now, how do we define continuity? What are the conditions for continuity? No. No, it has to be one-to-one. There has to be a function. In other words, which means that the function has to exist for any value c inside some closed interval. The limit of the function as x approaches that c has to exist. Now, we haven't finished this one. What does this mean? If the limit of the function exists as x approaches c, what does that tell us? The limit has to exist from both directions. And they have to be the same limit. So for the limit to exist, we have to check one-sidedness. Does it exist going from the left? Does it exist going from the right? And are they the same value? The last part of continuity says that the limit as x approaches c of the function has to equal the value at x of c, f of c. In other words, that tells you here the f of c has to exist, the limit has to exist, they have to be the same value. That's what this last part tells us. So that's continuity. If it's continuous, then it's differentiable, which tells us if the limit's continuous, then a slope exists at every point inside the domain. So let f of x be any function. Any continuous function. This represents the derivative of it, or I may write just f prime of x. I'll probably write f prime of x as my symbol notation. So the first one, if f of x equals c, some constant number, what is the first derivative? Actually, I'll put that over here. Think about it. F of the derivative shows us what? The slope. What is the slope of a constant function? What does a constant function look like? A horizontal line. Let's draw the graph here. Very good. Because no matter what x's you give me, the y's are the same. So if the y's are the same, the top is 0. So therefore your slope is 0, which is the derivative. So what we're going to do in this chapter, in chapter 2, we went through the whole gamut of epsilon delta proofs, then the proofs using the derivation of using the limit, the difference quotient. Now we're going to go straight into the shortcuts. And note, if something has been defined in class, you don't have to go through the whole process of deriving it. In other words, the next example. Yeah. Well, not really a property. It's just, it's defined. It's a definition. Okay, right? For example, if I gave you this function, if I said f of x is equal to 1 over x, what's the derivative? But if you don't remember it, you can always rework it out. How do we find the derivative? Remember, the derivative is slope, which we use a difference quotient. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. So to use this formula, what is f of x plus h? Right, so it's 1 over x plus h minus the original function over h. Now we have to algebraically fix the top. We have to get a common denominator. So this one multiplies x over x. This one's x plus h over x plus h. Distribute that negative sign on top. Combine like terms. Again, you have this in your notes from last class, so I don't have to go over step by step by step. So we have x plus h, negative h. This is compound function. Take the top fraction, leave it alone. Multiply by the flip of the bottom. Cancel. So we have negative 1 over x plus h. H goes to 0, so we have negative 1 over x squared. That's the derivative. Who thinks that's time intensive? Let me show you a shortcut. We'll do the same thing in about 3 steps. How can we rewrite this function? So x is now on the bottom. Remember, whenever you change the location of something across the dividing line, you change the sign of its exponent. So the derivative are you ready? Here it comes. Take the power, move it in front, and subtract 1 from the power. So we got negative 1. Negative 1 minus 1 is negative 2. There you have it. What does this mean? It means I put it on the bottom now. So on top, I have the negative 1 over x squared. We just did in this steps what it took us half a page to do. Yep. I'll show you. Because now we've never taken a derivative of a radical. Well, we have, but it took us even longer because we had to multiply by the conjugate. And that is a lot of step. So let's look at this example. If the function I give you is the square root of x, what's the derivative? Well, let's rewrite this. This can be written as what? X to the power 1/2. Because any nth root polynomial or a radical can be rewritten as that. Where the root is the denominator. So you remember the steps I just told you about? Take the power, put it in front, and subtract 1. What's 1/2 minus 1? Negative 1/2. Let's write this now in normal math. We have 1 over 2. This negative exponent tells us what? It goes on the bottom. Now the square root exponent tells us what? It's the square root of x. Remember, when we switch from square root of x to that, we're just going backwards now. So here's the power rule of differentiation. What does this mean? Well, how'd you read this? D dx means the derivative of x to the power n with respect to x. What this becomes, the derivative of this function, bring the power down and subtract 1 from the exponent. There's your first rule. There's your first shortcut rule. Do we have an example? Example 1. Find me the derivative of these functions. Using the power rule. So the first one, what's my first derivative? Which is 2. Think of how long that would have taken us in the past. Using the limit theorem, we have to do x plus h cubed minus x cubed over h. Now we just do it now step. How about the next one? Because you subtract 1, which is 3 over 3. 2 minus 3 is negative 1. Never leave your answer in a negative exponent. And there are a whole bunch of rules, algebraic rules here. You you never want to leave your denominator as a radical, because this one would look like 2/3 cube root of x. Remember, whatever's on the bottom, if you have a rational exponent, whatever's on the bottom is your root. So that is the cube root. And algebra says you're never supposed to have a radical on the bottom. So the computer will take these. If we were following those rules, what would you have to multiply top and bottom by? What's that? Nope. Notice, how do we get rid of this on the bottom? Well, we have to multiply. I'll show you right here. We had 1/cube root of x. We can't have a radical on the bottom. So what do you multiply by? Like that? No. Because if you multiply these, you'd end up with cube root of x squared. Nothing cancels. You need to have 3 x's. How many do we have here? How many do we need? Because now on the bottom, we have cube root of x cubed, which cancel, which gives us x on the bottom. So your answer would be cube root of x squared over x. That's just a side note. How about this one? Radical 2x. What's that? What's the rule? When you do what does it tell you to do with the exponent? Nope, square root of 2 minus 1. The formula says whatever you have on top goes in front and just subtract 1 from it. It's like this, as far as you go. I know, we want it to be more than that. It's just that it can be that simple. Because it's a radical 2, we have to have a calculator to do the actual decimals of it. How about D? The derivative here. Well, first off, change this one to what? Mm-hmm. And then that would be written as -4 over x to the 5th. We're doing shortcuts in derivatives. Here's the rule. This is called a power rule. Whatever the exponent you have on x, bring the exponent to the front and subtract 1 from the power. And that's what we're doing here. So what's this one going to be? -4 over 3. -7 over 3. Because when we take this one and subtract 1, which is 3 over 3, -4 minus 3 is -7 over the common denominator. So I don't know if the computer will take that or not, but since it gave it to us in the question, we'll leave it like that. Normally, we wouldn't. Mathematicians look at that and they cringe because we're not done yet. What this one should be is -4/3 x to the power 7/3. You get rid of the negative exponent. Now, this is an improper fraction. So 3 goes into 7 twice with 1 left over. Which is x squared x 1/3. Because I can distribute that, which is -4 3x squared cube root of x. It looks like an innocent question. But I would, after you do this, I would just try to plug this in the computer first. If it works, great. If it tells you to simplify, you have to go through all of this. It's still less time than it does to do the limit formula, the f of the difference quotient. So what do you have to do here first? Well, we can't take the derivative. How do we rewrite this one first? Exponential, right? So it's x to the power 2 plus pi to the power 1/2. Since you have a power to a power, you multiply them. So we have 2 plus pi over 2. And the derivative two plus pi over 2 x. Now we have to subtract 1, which is subtract 2 over 2. Pi over 2. Because here we have a common denominator, so the 2 and the -2 cancel, so we just have a pi over 2. A little bit more comfortable with it? I mean, this is going through the whole extreme of exponentials you can have. All right, let's go to the next rule. The derivative of a constant multiple in other words, if we have y equals 3x, when you take the derivative of this, don't worry about the 3. It's just a constant. Leave it alone. Take the derivative of x. What's the derivative of x? 1. So the derivative is simply the constant multiple. Now, here's a good question. You're absolutely correct. It is 1. Why is the derivative of x 1? Using the power rule. What's that? Very good. Because what's the exponent there? So the derivative says bring down the exponent and subtract 1. So we have 1. 1 minus 1 is 0. Anything to the 0 power is 1. So it's 1. So the derivative of x by itself is 1. How about this one? 15 x to the what? Very good. Forget the coefficient. The 5 comes down, and we have to subtract 1. 3 times 5 is 15, x to the power 4. What's that derivative? Hmm?
Isn't it x with a exponent of -3?
You have to first rewrite it like that. Now what do? Constant coefficient, leave it alone. Don't worry about it. Take a derivative of this one. Because you subtract 1. Which gives us what? And we can't have a negative exponent. So the answer is negative 15 over x to the 4th. Do we have any trig functions yet? No. Oh. What if we had that? Very good. So if the function is negative, it's going to end up negative, usually. Notice I said usually because we're going to show you the contradiction to that one statement. Negative 3 over x to the power 4. Now what? Yes, sir. So which becomes You remember I said, if your function is negative, it'll end up, no, it'll always end up in opposite sign if you have a ration. The derivative of a sum of functions. Of derivative of a sum rule or sum of functions. This is called the sum. So f of x and g of x are two continuous functions that are differentiable. Because if one of them is not differentiable, then we can't do this. So the derivative with respect to x of f of x plus g of x equals the derivative of f of x plus the derivative of g of x. For example here. Actually, this one, now it opens it up to polynomial that we can do it anytime we want to. Y equals x to the fourth minus 2x squared plus 2. Find the y, find the derivative. So we're basically what's telling us, how many terms do we have on the right-hand side? 3. 1, 2, anything separated by plus minus is a term. So we can take a derivative of each term separately. What's the derivative of x to the fourth? Very good. Which is just 4x. And then this one? It's a constant. What's the derivative of a constant? 0. It's a horizontal line. So constants disappear. But actually, let me put one here that has a whole bunch of pieces to it. Let's say 2x to the fifth minus 3x to the fourth plus 3x cubed minus 2x squared plus 5x plus 6. So what is it? What's the first one? Squared. That's it. Notice how if you just an x by itself, there's a single x, it disappears. If it's a constant, it disappears. You notice how the powers decrease by one. Seems that you guys are getting it. I put the wrong example 3 down. I took the wrong numbers. X cubed plus 4 over 3x squared minus 5x plus 1. Find me the derivative. Find the derivative of the polynomial. What did you get? Yeah, but 2 comes down, 2 times 4 is 8 over 3. There's a derivative. So what does this find again? The slope of the line tangent to the curve at a given point. Very good. That's going to help us for the next question. X to the 4th minus 2x squared plus 2. Does this function have any horizontal tangent lines? You have to understand what the question is asking. What is a horizontal tangent line? A horizontal tangent line. What's the slope of a horizontal tangent line? So how can we connect this with this? Well, first off, what is this graph going to look like? It's a fourth order equation. Because it's a fourth order equation, how many solutions may it have? 4 solutions, which means it can cross the x-axis 4 times. And since the degree is even, both ends point the same direction. Since the coefficient's positive, they both point up. So we can have 4 solutions because it's a fourth order equation, which means how many horizontal tangents can we have? We have to find those now. How do we find them? Very good. Find the derivative and then set it equal to 0. Because the derivative is your slope. So we got to find the derivative, which is 4x cubed minus 4x. So set that equal to 0. What do we have to do first? Factor out the 4x, which gives us x squared minus 1. Can this be broken down any further? It's a what? It's a difference of two squares. So it's x plus 1, x minus 1. Very good. So what are my solutions? Set them all equal to 0. So it's x equals 0 is the first one. So these are the x values where the vertices exist. So looking at our graph, we know at -1, +1, and 0, we have a vertice. So what are their points? If we plug in these points into this equation, we plug in 0, we get 2. So that's going to be the highest point. If we plug in -1, minus. So it's 1 minus 2 plus 2. So y equals 1. That means 1 equals 1. This is what your graph looks like. We have a vertex there, a vertex there, and a vertex there. Vertex is where the graph has a horizontal tangent line. Do you have any more examples there? No. So far, so good? Derivatives of exponential functions. Where a has got to be greater than 1. Let's use b for base. The base has got to be bigger than 1. So the derivative of an exponential function. How do you think we go about doing this one? We can't really do anything because it's an exponent right now. So how do we get rid of that? Well, do we have, with anything in our arsenal, we could take the log. If we do that, we take the log of both sides, or ln of both sides. Ln y equals x ln b. Now we have ln y. Okay, we could do that. It would just be a very long, drawn out process because then we have to get rid of the ln. So what's another way of doing it? If worse comes to worse, we fall back to one of the ones we did in the past. Limit proof. The limit f of x plus h minus f of x Can we do it with this function? For this example, let's make it a 2 to the power x. Let's look at this. So what is the f of x plus h? So it's going to be 2x plus h. So that's y sub 1, that's y sub 2. So we have our limit as h approaches 0 of the first one, 2x plus h minus 2x over h. So what rules do we know? How can we expand these? Remember the rules of exponents. If you have the same bases, what do you do with the exponents? Add them. We start off here. Let's break them up. We have 2 to the power x times 2 to the power h minus 2 to the power h. Yeah, because we have an x there and an h there. Oh, h, yeah. Thank you. I was trying to remind myself, don't forget the h on the bottom, and I forgot the h on top. I put the. So what can we do now? For the rest of these, I'm gonna go straight down. Can we factor anything out of the top? So they both have a 2 to the x, which gives us 2h minus 1. What can we do now?
One range.
If we just plugged in 0 for h, what would happen? Two to the 0 minus 2 to 0 is what? 1. Anything to the 0 power is 1. So I have 1 minus 1 is 0. 0 over 0. So yeah. So remember, whenever we have a limit of 0 over 0, we can try that. We can try the conjugate. Let's see where that would take us. We have 2h plus h plus 2h minus 2h minus 1. Okay, we did that. Now what do we do? It's hidden in there. You just have to see it. This one? How? Because if the top, we're still stuck at 0 over 0. So it's an infinite loop. So the derivative of 2 to the x is 2 to the x. It stays the same, it doesn't change. Because no matter what happens in there, no matter what we do to it, it's always going to stay the same. But that's if it's just an x. What if we had a coefficient in front of our exponent? Because now we have to take a derivative of that. What's the derivative of 3x? Times the derivative of this whole thing is 2 to the power 3x. No, it wouldn't be 6 because this is an exponentiated term. So it's 3 times this. In other words, if you have, it's easier when we do with ease because that's just, it's not a physical number. But if A is any base greater than 1, the derivative would be the derivative of u, AU. Likewise, when we deal with this, or as we commonly say, EU du. Example 5. It says, find the equation of the line that is tangent to the graph. Find the equation of the line tangent to y equals e to the x. Going through the origin. To find the equation of a line, what do we need? we need a point, and we need a slope. Do we have a point? If the line goes through the origin, what's that point? Do we have a slope? Yeah, that's the y derivative. So the derivative of e to the x is e to the x. So that's my slope. But what's missing? We don't have a value for a slope yet. We can't use 0, 0. Or can we? Think about that. We're finding the equation of a line. We have to know the slope. So this has to be a value. And it has to go through the origin. So we need an x value. What x value do we use? 0. Because if it's the equation of a line, it's going to have the same slope everywhere. So we're going to say x equals 0 from the origin. So my slope is e to the 0, which is 1. Going through the point 0, 0. Do we have a y value? Right here. Do we have an x value? Yes. We have an m. So we have 0 equals 1 times 0 plus b. So b is equal to 0. So the equation of the line, the slope is 1 and the y-intercept is 0. Is y equals mx. Is simply the 45-degree angle line. What if we had a constant multiple? What we're saying is this. What's the derivative going to be? Well, it's a constant, so leave it alone. What's the derivative of e to the power x? There's a derivative. So if the function was 3 e to the power x, the derivative would be 3 e to the power x. If the function was 3 e to the power 2x, the derivative would be yeah, so beautiful thing about the e value, the derivative will always have the original e value in it. Only thing that's going to change is the coefficient. The product rule. Product deals with what? Multiplication. So the derivative of f times g is equal to the derivative of f times the derivative of g. Which is, because it's a product, which is the g df plus f dg. This is the formal definition for it. Let me show you a shortcut. If you have a function that's made up of two parts, let's say y equals that. Think of it this way. First, put your functions here. And then take their derivatives. Product multiplication makes things bigger. So in this case, we add. Start from your g of x and make that big fishy thing. And since it's product, we're going to add. So what it's telling us is g times f prime plus f times g prime. That's what it's telling us. That's the easier way to look at it. Because it's also going to help us when we do the quotient rule. Let's look at an example here. So remember the fishy thingy. We do fg, f prime, g prime, and do the fishy thingy. From the top right, example 6. A, y is equal to 1 over x, x squared plus ex. Is this a product rule? Do we have two functions? Yeah, we do. Here's the first function, that's f, and this is g. So f is 1 over x, which is x to the power negative 1. G of x is x squared plus e of x. On the bottom are the derivatives. The derivative of 1 over x is very good. And then the derivative of g prime. Here we have a sum of two numbers. What's the derivative of x squared? 2x. Plus, what's the derivative of e to the x? Now we do the fishy thingy. Since it's a product, we're going to add. So the derivative is x squared plus e to the x times -1/x² plus 1/x times 2x plus e of x. And go ahead and simplify that. It's negative, so we distribute the negative and divide everybody by x squared. So we have x squared times -1/x² plus e to the x times -1/x². Same thing here. 2x times 1/x plus e to the x 1/x. Algebra. So it's negative e to the x squared and x² cancel, so it's -1. Negative times positive is negative. E to the x/x². The x's cancel, so it's 2 times 1 is 2. Plus e to the x/x. Combine like terms. -1 plus 2 is 1. E to the x/x² plus e to the x/x. What's that? Where's 1/x?
Negative. That's.
Yeah. We now multiply by x/x, all of them. Get a common denominator. So x/x, x/x. Oh no, this one has to be x²/x². So it gives us x² minus e to the x plus x e to the x all over x². There's your answer. There's your derivative. There are a couple ways you can write it, but this is the most simplified form. And the other one was e to the 2x. So that's your answer. That's your derivative. Let's try e to the power, the next one, b. Using the product rule. Using the product rule. What does that mean? How do we do that with this? This becomes e to the x times e to the x. Because if you think about it, when we same basis, add the exponent, x plus x is 2x. So this is f and this is g. So it's e to the x, and that's e to the x. What's the derivative? And we add. So we have e to the x times e to the x plus e to the x times e to the x. E to the x times e to the x is what? Well, it's e to the 2x plus e to the 2x. So then we have two of those. That was, of course, the long way around doing it, but it said, let's use the product rule. If you saw this, remember the shortcut? Take the derivative of the exponent, which is 2 times whatever the function is. Let's look at quotient rules now. Is there another example for a product rule? No. Okay. Quotient. Let's, when we define y as f of x over g of x, of course, g of x cannot be 0. The derivative here it's going to be the same thing. But remember when we, okay, let's go backtrack a little bit. When we took a derivative of 1 over x, what did we get on the bottom? X squared. So whenever you take a derivative of a quotient, the bottom will always be squared. It's always gonna be squared. We saw that from the 1 over x rule. Now, so that's whenever you have quotient, it's always gonna be squared. Whatever's on the bottom. We do the same thing we did last time, but division makes things smaller. So we subtract. So we do g of x times f prime of x, g of x f prime of x, minus f of x g prime of x. Those two. You won't see this anywhere. Actually, I developed this a long time ago when I was instructing students so they can visually see what's happening. And the most easiest thing people remember is that fishy thingy. So this is proprietary to me. So let's look at an example. No, I should do it. But again, in academia, we don't care about, we can't make any money off it. So here we have example 7. Here's A. Y equals t squared minus 1, t cubed plus 1. I'm going to use x's instead of t's. I'm not going to use t's because my t's eventually look like pluses and I get confused. So here's my f and there's my g. So the f function is x squared minus 1, x cubed plus 1. So what are the derivatives? Do this one?
Oh.
And then this one? So the derivative is going to be x cubed plus 1 times 2x minus x squared minus 1 times 3x squared. All over the bottom squared. Let's get rid of the parentheses. So we have 2x times x cubed, which is 2x to the 4th. 2x times 1 is plus 2x minus 3x squared times x squared is 3x to the 4th minus 3x squared. I needed to put this in brackets because that minus sign is still out there. I just multiply these two together. Because my next step is distribute. So I distribute, I get negative 3x to the 4th plus 3x squared. Combine like terms, we have 2 minus 3 makes it negative x to the 4th plus 3x squared plus 2x. Can we simplify it? Well, the only way we can simplify it if we could break the top down to 3x cubed plus 1. And it's not going to happen since it's a fourth order equation. All we can do is factor out an x, and that won't get us anywhere. So we're done. Yes.
What if you had split the numerator into two and then use three functions instead of just two?
How do you mean?
So the original was y is equal to t squared minus one
Right.
over t cubed plus three. So what if you numerator is a difference of two squares, which would be t plus one and t minus one.
Right.
What if you had used three functions to do?
Oh, you get the same thing. Oh, actually, it's a question. I'll show you what we mean. Yes, let's try that. That's a good question.
What I was gonna ask is, would it be easier or harder?
It'll be a lot more work. I'll show you why. Hard work. We have x squared minus 1 over x cubed plus 1. So we're saying here is x plus 1, x minus 1. That's a good thought. Let's see how it works. Because now, remember, this is still our f and this is still our g. We have the f prime g prime. So f is x plus one, x minus one. G is x cubed plus one. I don't know why I put parentheses around them. The derivative, we now have to do the product rule here. So this is f and this is g. So here we gotta look at x plus one, x minus one, so it's 1/1. So it's gonna be x minus one times one plus x plus one times one, which makes it x minus one plus x plus one, 2x. So right there, automatically, it's a little bit more work you have. So then now from here, we have our f prime, we have our g prime, we have now we can do the fishy thing. And so you see automatically here, it's going to start this times this, so it's 2x times x cubed plus 1 minus 3x squared times these two, x plus 1, x minus 1. It's not more difficult. It'll give you the same answer. It's just a lot more writing. But yeah, I'm glad you saw that though. Because what the first thing you want to do is if you have polynomials of degree order 2 or higher, see if you can cancel anything. See if you factor this one out, see if you can factor this one out, see if they have something in common. If you cancel that out, then it makes it much easier. B, y equals e to the power negative x. Is that a quotient rule? Because it's a negative exponent, it's 1/e to the x. We wouldn't do this in our right mind. I mean, we just take the derivative of this would give us what? Negative, the derivative of that is -1 times e to the negative x. We know that's the answer. That's what it's supposed to come out to be. But let's look at it if we use the quotient rule. I don't know why, but they want us to do that. This is f and this is g. F is 1, g is ex. The derivative of 1 is 0. Derivative of e of x is e of x. So we get e of x times 0 minus e of x times 1. All over e of x squared. Because that's the bottom. So that's 0. So we have negative e of x over e x squared. Can anything cancel? Which is -1/e of x, or -1 e to the power negative x, which is the same thing we got. Because that's why we have the square there, because now this and one of those can cancel. What do y'all think so far? Is this a lot faster than the limit and the epsilon delta proof stuff? Yes. Let's look at example 8. The function is x minus 1 times x squared minus 2x over x to the fourth. How would you go about doing this? How do you mean?
Like instead of doing two functions.
Okay, yes. Why wouldn't we do the quotient rule? But you're right, because if we did a quotient rule, now we have to do the product rule like we just did. But if we multiply them together, then we only have one equation and just do it once. Okay, let's do that. So x times x squared is x cubed. X times positive negative negative, 2x squared. Negative x squared, positive 2x. I foiled those. Combine like terms, you have x cubed. Negative 2x squared minus x squared is minus 3x squared plus 2x. Now here's a shortcut. Because the denominator is a monomial, only one term. We could break them all up into smaller pieces. If your denominator is a monomial, then you're right. We multiply the two tops together and then let's divide each one separately. Because this one will give us threes cancel, so we have 1 over x. Two of them cancel, so I have x squared on the bottom. One of them cancels, so I have x cubed on the bottom. Do we have to do the quotient rule? No. Because each of these are monomials. So the derivative of each one of these separately, derivative of the first one is negative 1 x to the power negative 2. What's this one, next one going to be? Positive 6x to the negative 3, because you subtract 1. Negative 4. Very good. Which means I have negative 1 over x squared, positive 6 over x cubed, minus 6 over x to the fourth. And there's my answer. So you see, you have multiple tools at your disposition now. Whatever you think is easier for you to do, use that tool. Any questions about that so far? The beautiful thing about derivatives is there's no limit. The limit is only dependent on the function itself of how many derivatives we can take. What's the first derivative? Okay, let's look at the second derivative. Remember, bring the power down, subtract one. It's the same rule over and over and over. Just repeat the process. The third derivative. The fourth derivative. 24. Yeah, because x disappears. And the fifth derivative? 0. What's that? Well, you can't derivative of 0 doesn't exist. So fifth degree is as far as we can go. There are functions. Well, look, for example, 1 over x. Let's look at the first derivative of that one. Equals what? One of those. It's a 2 in there somewhere. Okay, then what's the next derivative? So we would take this one. We would write that one as -2. So the power, this one comes down, makes it a power +2. So we have 2 over x3. The third derivative. This one's 2x to the power -3, which makes it -6 x to the -4. So you see what's happening here? The numerator changes from positive, negative, positive, negative. It alternates. The denominator increases. Does this one have an end of how many derivatives I can take? Nope. Example 9. Y equals x cubed minus 3x squared plus 2. Find the first 4 derivatives. So the first derivative is what? Everything's gone. Second derivative. Yeah, because x disappears. Third derivative. Fourth derivative. That's how you do it. And we basically, what this is saying, we can go on to any nth order derivative. And the last page of your sheets are different symbols we can write. Double prime or, and we'll have exposure to these. Nah, we don't. The next part, the next section deals with derivatives as rate of change. In other words, we're now going to look at derivatives with respect to like physics or engineering or mathematics and derivatives in business. They each have the same process. They're called something different. And that's what we'll talk about next. What's today, Wednesday? So I'll see you on Monday. Have a great, safe weekend. Okay. Unfortunately, this chapter has 9 sections. And we'll try to finish them next week. If not, then we'll do it next week after. But yeah, I'm gonna start showing